So I will try to speak slowly, but if I'm too fast and if people have difficulty in understanding, please ask me to slow down or repeat something either in the chat box, or you can tell to Hong Chao and he can tell me. All right. So I would like to begin with the plan of this mini course. I'm going to talk about the gravitational waves and their properties in exact general relativity. So in part one, I'm going to focus on conceptual and mathematical issues associated with gravitational waves in full nonlinear general relativity. So this is different from the approximation methods that you have been studying in other lectures, and also different from numerical relativity. These lectures will provide kind of the foundation for the concepts and the mathematical tools or mathematical notions that are used in the approximation methods like post-Newtonian methods, and also the conceptual tools that are used in numerical relativity, some of them, not all of them, but some of them. And in the second part, we'll see how results in exact general relativity can be used as diagnostic tools to test the accuracy of the waveform models. So there are various model waveforms. You might have heard about it in other lectures, and we will see how these precise mathematical results that we have in full nonlinear general relativity can be used to do this, as a diagnostic tool to test how good the waveform models are and also to improve them. Now, normally one uses numerical simulations to evaluate the accuracy of this of the waveforms, but there are regions in the parameter space. Where the numerical simulations are sparse. There are not enough numerical simulations for certain values of the parameters, the binary. And then, however, the diagnostic tests that I'm going to discuss, they come from identities that must be satisfied in exact general relativity. No matter what your method is, if your model is a good approximation to exact general relativity, it must satisfy these identities. Therefore, they can serve to test the accuracy of the candidate waveform model and suggest directions for improvements in all regions of the parameter space, even where the numerical simulations are very few. Furthermore, they can be also used to test the accuracy of the numerical relativity waveforms themselves. So I'm going to give you the main references, and for lecture one, these are the main references that I understand that the slides will be available to you over the weekend, so you can look at those references. I'd also send them early on. Okay, so what I would like to begin with the following. Really, the question is, what do we mean by radiation content of a solution to Einstein's equations? Now, this is very difficult to identify. And that led to a lot of confusion about a reality of gravitational waves in full nonlinear general relativity in the early days. And we will hopefully see this confusion at the end of today's lecture. But even Einstein himself contributed to this confusion. But this was clarified in the 1960s and 70s by Bondi and Sachs, Newman, Penrose, and others. And some aspects of the confusion are present already for the Maxwell fields in Minkowski space. And so in this lecture, I want to begin in this simple case of the electromagnetic waves. I think you all know about electromagnetic waves, so I hope this will be a good bridge between what you know and what we're going to learn new. And now what we'll do is this discussion will provide intuition and techniques for gravitational waves, which we'll then study. And again, I repeated here the references that I had given before. So now what we're going to do is the following. We're just looking at Minkowski spacetime, and we're looking at Maxwell equations. So therefore, we got a Maxwell field FAB, skew symmetric second-rank tensor field. And it satisfies the equation that the curl of F is equal to 0 and the divergence of F is given by the matter current, the charge current. What we're going to assume is that this charge current is non-zero only in some spatially compact region. We're going to assume we're interested in isolated bodies, so the two charges or three charges might be interacting with each other in some region of space-time, in some finite region of space-time, spatially finite region, and we want to know about the radiation that emits. So the main issue here is that we cannot extract what we mean by radiation content of the Maxwell field at a finite distance from the sources. So there is no local criterion. This is a key point. There is no local criterion to know what you mean by electromagnetic waves or how much radiation there is in a given solution FAB of Maxwell's equations. We cannot determine it locally. Now, this might come as a surprise to you, and it comes as a surprise to many people, because you would say, but we got pointing vector, which you can use to calculate the flux of electromagnetic momentum, for example, across some two-dimensional surface. So one would say that if the pointing vector E cross B is not equal to 0, then there is radiation. And this is a local condition. But it turns out that this is not true. This condition is not invariant under Lorentz transformations. So for example, you can take just a point charge just sitting somewhere on the table, just is a point charge. And then it's in the rest frame of the charge, I got electric field and I got magnetic field. The magnetic field is 0 and the electric field is just a Coulomb field, the charge upon R squared times R hat. And of course, because this is B equal to 0, then E cross B is equal to 0. But if you boost this charge in the Z direction, then you will find that I get a new E prime and a new B prime, and you will find that E prime cross B prime is not equal to 0. The pointing vector in a new frame is not equal to 0. So this is just a charge is just sitting there, and we're looking at its pointing vector, and in some frame it is 0, in some frame it is not equal to 0. So we cannot use this as a criterion of whether there is electromagnetic radiation. We need something that is an invariant criterion. And whenever I say X and this purple color up here in the slides, it always refers to exercises. And I urge you to do these exercises to be able to understand this subject as well as gravitational waves in general clearly. So the question is, what is radiation? And radiation is really the 1 over R part of the field. But to extract the 1 over R part of the field, obviously, I cannot just look at a given solution locally in a little region of space-time and ask for whether it has 1 upon R part. That doesn't make any sense. We need to go to the far region, do a 1 upon R expansion, where the 1 upon R expansion is good. And then we can actually say that in the far field region, we can try to extract the 1 upon R part of the field, and then that would encode the radiation. So mathematically, this corresponds to R going to infinity, and this is a global concept. And there is a precise way to do this global concept up here that I'm talking about, how to extract it. And that is given by Penrose's conformal completion of space-time. So I just have Minkowski space because we are looking here at Maxwell field in Minkowski space-time. So I got this Minkowski space, manifold is R4, Minkowski metric of minus plus 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 signature. It is just the standard flat metric that we got up here. And so what we're going to do is the following. You take this Minkowski space, and we're going to be interested mainly about, supposing there are some charges here which are radiating. We're interested in how much radiation is there, or can we identify radiation in an invariant manner, gauge invariant, Lorentz invariant manner. And the idea here is that because radiation travels in null directions, and we're interested in retarded fields, so let's use a retarded null coordinate u t minus r. And the advanced null coordinate will be t plus r. But at the moment, I'm going to focus on just t minus r. And then I can just write down the Minkowski metric, which is just minus dt squared plus dr squared plus r squared times the two sphere volume element, which I call just d omega squared from now onwards. And now what I just do is to substitute for this t is just equal to u plus r, and plug it in here, and I get this metric to be minus du squared minus du dr squared cancels from dt squared has a minus dr squared, and then this dr squared they cancel, and I get plus r squared d omega squared. So as r goes to infinity and u goes along u equal to u naught, if I go like that along u equal to u naught, as r goes to infinity, this is r equal to 0, and I just go along r equal to infinity, then the metric is ill-defined. But what we can do is to bring infinity to finite distance by this conformal transformation of Penrose's and carry out a conformal completion. We do this by defining a conformal factor omega to be equal to 1 upon r. So r equal to infinity corresponds to omega equal to 0 up here, and this would be the omega equal to 0 surface now. I brought infinity to a finite distance by this conformal transformation. But this metric, of course, is badly defined at r equal to infinity because of r squared term up here. But what I can do is to introduce this omega as a new coordinate, and I can rescale the physical metric dA squared we have got with this omega squared and construct a conformally rescaled metric, omega squared times dA squared. And that then just becomes omega squared times that thing, plus du dr, this r, when I replace it by d omega, I get 1 upon r squared. That cancels with this omega squared. So I just get du d omega, and then I get d omega squared up here. So therefore, this metric ds hat squared is perfectly well defined if you think of your coordinates to be now not r, but omega. If you think of u omega theta phi as your coordinates, then this metric is perfectly well defined. This term just becomes 0 at omega equal to 0. But this is a non-degenerate metric because of du d omega term up here. These are, and so therefore the statement is that I got a well-defined metric of signature minus plus 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 in a neighborhood of omega equal to 0. Of course, omega equal to 0 is not a part of Minkowski space because r equal to infinity there. So what we have done is attached a boundary. We have brought infinity from far away to finite region by this conformal transformation, by this Penrose completion, and now infinity is arising as a boundary. And this boundary is called scry plus. Scry is for script I is called scry because script I is short form, and plus means I'm using retarded coordinates. I'm going to future, and that is why it is plus. If I had used v as my coordinates instead of u, if I had used v, then I would be going along v equal to v naught, and that would be advanced coordinate up here, and then I would go to past infinity, and that will be called scry minus as it is written here. So currently I'm just focusing on scry plus. So at scry plus, the 4-dimensional metric is just given by this, and this symbol always will mean equal with a hat, just means evaluated at the boundary points, either scry plus or scry minus, most of the time at scry plus. So the tangent vectors to scry plus are going to be d by du, because here omega is equal to 0. My coordinates are omega u theta phi, and omega equal to 0. So I got these 3 coordinates, u theta phi. So my vectors tangential to scry are going to be equal to d by du, d by d theta, d by d phi. And this vector d by du is a null vector because you can see here explicitly from this metric that if I just move along du direction, I will get just du squared. Then I don't get any contribution at all. I just get, there's no du squared. Therefore, if I take the metric g hat ab and put here ua ub or d by du, d by dub, I just get 0. Therefore, this is a null vector. And therefore, although scry is 3-dimensional, it is coordinatized by u, theta, and phi. The intrinsic metric if I pull back the metric to scry, if I just contract only with vectors, if I contract only with vectors which are tangential to scry, then I find that the metric is just the two-sphere metric and it is degenerate. We can use the advanced null coordinates, as I said, and then that will take us to scry minus up here. Now, there is a null tetrad, and that is a convenient basis to expand fields. And this was given by Newman and Penrose. What I can do is to take T minus R and take its gradient, and that would give me a covariant vector. T plus R, take its gradient. These are two null coordinates, retarded null coordinate and advanced null coordinate. And then I will get, these two are null vectors, therefore. And now what I do is I take a complex linear combination of d by of grad theta and grad phi, and make this also a null vector. In other words, GAB, MA, MB is equal to 0. And similarly, GAB, M bar A, M bar B is also equal to 0 everywhere. And therefore, what I get is 4 null vectors, N, L, M, and M bar. And their norm is 0, they're null vectors. And in fact, though N is perpendicular to itself, is also perpendicular to M. L is perpendicular to itself, is also perpendicular to M. And M and M bar, and M is of course null. And the only non-trivial inner products are N dot L, which is minus 12, and M times M bar, and that is equal to plus 1. All other contractions vanish. Therefore, for the rescale matrix, omega squared times theta AB, we have to rescale this triad, and the rescale triad is given by N hat A. So when I raise the index of NA up here, I'm raising it always with respect to the physical metric GAB. Whereas when I raise the index of the hatted quantities, I'm always using them with a rescale matrix N hat B. So you can check that this object has a well-defined limit on scry. This object has a well-defined limit on scry. So there are some conformal factors that come up here, which are just because the two metrics are related to each other by this conformal transformation. And similarly, M hat is perfectly well-defined at scry. So we get this hatted null tetrad, which are well-defined with respect to eta hat AB everywhere, including at scry. And now the point is that we can use these null tetrads in a very effective way. The conformal invariance of Maxwell's equation, it says that if I set f hat equal to f, then curl of f hat is also 0. This can be the grad hat derivative operator. It doesn't actually matter which derivative operator you choose. And similarly, I got here the divergence of f is also given by current. That current is related to the physical current by omega to the minus 2. And so the statement is that I got, but since we had assumed that the current is all the sources are in some finite region up here, therefore omega here is not 0, omega is just 0 here. So omega to the minus 2 is perfectly well defined. And this is also a smooth field, and it also has a compact support. So it's spatially compact because J is spatially compact. Therefore, that is true. And therefore, scry is a regular submanifold in the completed spacetime. And f hat AB is a solution to Maxwell's equation. So with respect to the completed spacetime, I got some sources up here. I got some sources here. And this is just a finite surface in the completed spacetime. And therefore, of course, the retarded field here is completely well defined because I got some smooth sources and I'm just looking at a finite distance, and therefore f hat AB is completely well defined here. So f hat AB is completely well defined, and therefore, but f hat AB is equal to FAB. So these are completely well defined tensor fields at scry, and therefore we can calculate the components. I can take the null tetrad components. Since I got FAB as 6 components, which I can express these components in terms of 3 complex quantities, which are called phi 0, phi 1, and phi 2. And these quantities up here are just various contractions with the null vectors, the null tetrad vectors of the metric eta hat AB. These are the null vectors of that metric. which are perfectly well defined at scribe. So this is well defined at scribe, and therefore I get the hatchet quantities are well defined on scribe, and therefore I know that this quantity is perfectly well defined on scribe. Therefore, if I now take the physical FAB and physical null tetrad, these physical components of the null tetrad up here are going to be given by these quantities, which are perfectly well defined upon R. These quantities, the R just comes because M is equal to M hat upon R. N is the same as N hat. L is equal to L hat upon R squared. M is 1 upon R, M bar is 1 upon R. Therefore, here I get 1 upon R squared. And because I got 1 upon R and 1 upon R squared here, I get here 1 upon R cubed. So the statement is that what I find is the physical components in the null tetra or the Maxwell field, they at infinity fall like 1 upon R squared, and 1 upon R cubed. And that just follows from the rescaling of the physical null tetrad and the conformally completed null tetrad. These are well defined. So these quantities are all well defined. F hat is well defined. Therefore, this quantity is completely well defined. And this quantity is completely well defined. Therefore, that quantity is what I'm calling phi 2 naught. Therefore, I know that the physical quantity phi 2, phi 1, and phi 0, the physical components, the physical tetrad, in the physical null tetrad, they fall like 1 upon R, 1 upon R squared, 1 upon R cubed. And this is called a peeling property, because this part falls like 1 upon R squared, so it peels off as 1 upon R squared. Then if you want to dig deeper and find the part which falls like 1 upon R squared, then you have to look at that. 1 upon R cubed, you have to look at that. As a side remark, if I use a potential for the Maxwell field, then if I use a gauge in which the n component of A hat is equal to 0 at scribe, then one can show that the Li of this, which is the same as d by du of A dot M bar, is just equal to phi 2 naught. So A dot M bar has 2 real components, and phi 2 naught also has 2 real components, as you can see here, because it is complex up here. Therefore, it has 2 real components. And these are the radiative modes which fall off like 1 upon R. So we return to the question that we began with. How do you talk about the radiation content of the Maxwell field, the 1 upon R part of the Maxwell field? And the point is that in a local region in space-time, if you just give me the Maxwell field and ask for 1 upon R part, I don't know what 1 upon R part is. But if I go to scry null infinity, if I conformally complete this space-time and add to this boundary, then I know that some part, like phi 2 naught part up here, that part is a radiation field that it has 2 components, and I can extract the radiation field in that way. This part, phi 1, is phi 1 naught upon R squared, and therefore you would imagine this to be the Coulombic part, because the charge is always obtained by taking E dot ds and taking integral, and similarly magnetic charge will be B dot ds and taking the integral. Magnetic charge generally vanishes, but you've got the electric charge in general. And the point is that is therefore obtained, all the information of the charge is all contained in this phi 1 naught. So therefore the Coulombic part is in phi 1 naught and the radiative part is in phi 2 naught. Phi naught naught, the last component, falls like 1 upon R cubed, and it has information which is less interesting because it is really higher order information. It's useful, but for our purposes, it is less interesting. And therefore, the energy angular momentum of electromagnetic waves can all be expressed using this phi 2 naught. If in fact phi 2 naught equal to 0, then the field, there is no emission of energy or angular momentum by sources. If I have sources like that, and if phi 2 naught is 0 here, then I will just say that there is no energy that is radiated, there is no energy that is lost. If phi 2 naught is not equal to 0, then as we will see in 1 minute, we will see that this electromagnetic waves or electromagnetic field carries energy and momentum and angular momentum across null infinity, away from the sources. So to summarize, we start with this question: can we talk about the radiation part of the electromagnetic field? And by going to scry, we can compute certain components of the electromagnetic field, and that component, this particular component, is the radiative part. We will see that the same thing is true in the gravitational case, and that is why people calculate. You might have already heard it. People calculate in numerical relativity what they call psi4 naught, and that psi4 naught is completely analogous to this phi 2 naught, as we'll see in the second or third lecture. So there's an exercise here. The exercise is really for you to check that the peeling property holds. We know this is well defined, so all you have to do is to substitute n and m bar in terms of the conformal rescale fields, which are well defined, and that will tell you how this component falls off. It falls off something which is well defined at r equal to infinity upon r. This falls like something which is well defined at r equal to infinity upon r squared, etc. So this is your second exercise to check that this peeling property holds. And now we return to the question that we already did that. It began with that 1 upon r part is isolated in here. So now we can talk about the energy and angular momentum carried by electromagnetic waves. And they're all expressible as integrals on this Scri plus. Again, I'm interested here in waves which are I got some sources in the interior region, and they're radiating waves. I'm looking at retarded solutions, and these waves are registered as Scri, and therefore energy and momentum they carry away is registered as as integrals on Scri here of some quantities, as we will see in a minute. So let's see how that works in a second. But to do that, first let me just do the following. Here I was looking at RT plane. This was going R and this was going T. So I was suppressing theta and phi. Each point in the interior here is just a theta and phi. What I would like to do is to expand it out. So if I expand it out, I get the picture would look like that. If I rotate it around, of course, I cannot draw a 4-dimensional picture, so therefore this picture is not so good. But it is 1-dimensional suppressed, so you have to think of this as being not a circle but a 2-sphere, and then you get a picture which looks like this. We get a picture like this. Scri here, Scri plus will be here, Scri minus will be here. You'll get a picture like that, and then I got a 2-sphere cross section. So this Scri is a 3-dimensional surface. Up and down is u coordinate, and here the 2 spheres around here of Scri are the theta and phi coordinates. So u is equal to u naught constant. So along a 2-sphere here, u will be equal to u naught, and I'll get theta and phi running on these coordinates up here. So therefore the picture will look like that, right? I mean, like Scri plus is here, Scri minus is like that. Now in this picture, I'm not good at drawing, but if you can think of the surface, which is just t equal to 0 surface, is a space-like plane, x, y, z coordinates, t equal to 0 surface, that looks like that. If I were to boost this surface, then I will get a surface like that. If I were to look at a, sorry, not boost, if I were to look at a time translated surface, so this t equal to 0, t equal to t0 up here will be a surface which will look like that. Let me try to draw it better. So this is a plane. It is again coordinated by x, y, z, and t is equal to t0. And if I take the limit as t0 goes to infinity, then these surfaces approach Scri. Or I can approach Scri in another way. I can go in the physical space-time. In the physical space-time, I can consider a cylinder, and this cylinder is going along t in this direction, and what is constant is really r. So r is equal to constant here, and I got here t or u if you like, and theta and phi running along that direction. So in this conformal diagram, these cylinders look like that. And I can also take this cylinder to infinity, just take this cylinder to infinity. So here in this picture, I take the cylinder to infinity, r goes to infinity if you like. If I do that, actually, I also can go to Scri. So I can go to Scri by either taking space-like surfaces, and I look at how much energy is crossing the space-like surface and take the limit to Scri, or I can take a cylinder, a large cylinder at r equal to constant, r equal to r naught, and take as r goes to infinity, and then I will approach Scri and I'll get an integral up here. Now you all know that the flux of various quantities are also the Killing vector field. The Killing vector field is a time translation, d by dt. Then this flux will be the energy flux. If the Killing vector field is d by dx, then the flux will be 3 momentum flux, or x component of the 3 momentum flux. If it is d by d phi, the Killing vector field, then I will get g component of angular momentum. So you all know that I can take stress in a tensor, plug into the Killing vector field, and integrate on the surface, like for example, t equal to t0 surface, or I could integrate also along r equal to r naught surface. I just, for the definiteness, I just use this, and then therefore, if I use this surface up here, then I will get this unit normal is going to be TA. TA is just the Killing vector field, and this is the XYZ surface, t equal to t naught, and so I can calculate this energy flux that goes through this surface or to this surface up here. And you know that the stress in a tensor is given by FF, contracted on M and N indices, minus the trace of this quantity. And therefore, you can calculate this quantity. And as an exercise, you calculate this and show that for energy, if you take the Killing vector field to be a time translation, then for energy, this integral just gives you integral of phi naught squared. And phi naught is the object that was obtained by this phi naught, by taking F and plugging into M hat and M bar hat. So what you have to do is to just expand this out, FAB, expand out this GMN. The GMN, the full metric, that is given by minus 2 times LA NB. These are these orthonormal tetrad, sorry. So the metric eta AB, not GAB, eta AB is given by 2 times is equal to 2 times LA NB, and then plus MA M bar B. So you got a metric like that. So you can just take the metric, substitute in here, and then you will get components up here of the triad. This, you got this TA, so you can write down this TA in terms of NA, and therefore TA is equal to NA, and then you will find this. And similarly, you can take d by dx and calculate this integral, and you will find this integral up here. So in this case, what I've done is, for simplicity, I've taken the z directional Killing vector field, and therefore what you get here is cos theta. If I take an x directional Killing vector field, instead of cos theta, I'll get sine theta cos phi, which is like the unit radial vector projected along x-axis, or along y-axis, sine theta sine phi, or along z-axis, just cos theta. So this is really are the components of a unit radial vector in Minkowski space. That they are just angles. Cos theta, sine theta, cos phi, sine theta, sine phi. So that is what we get. And now, in addition to that, what we see therefore here is that, in fact, indeed, it is the case that the energy flux and the momentum flux all are given by just phi to naught. If phi to naught is equal to 0, then the Maxwell field doesn't carry any energy or any momentum, x or y or z component of the momentum. And the same thing is true with angular momentum. If phi to naught is equal to 0, the flux of angular momentum is also 0. But I also said that this quantity phi 1 naught, this phi 1 naught is 1 upon r squared, and that is the Coulombic part. And indeed, we can therefore hope to get the charge in terms of that, and that is exactly the case up to a numerical constant. If I take the real part of phi 1 naught, and integrate it on this cross section, so here is Cry. I take any cross section u equal to u naught. Charge is conserved, so you can take any cross section you want, and then you just evaluate this quantity, and so you know the electric what the charge is. So you can just use the expression of the charge. Charge is given by if you like, it is given by FAB times TA. So it is given by just the radial component of the electric field. So charge integral in the physical space time will be given by FAB times TA times unit radial vector times d2s to 2-dimensional region. And you can just take these vector fields, convert them into the null triads and null tetrads, and you will see that you get this. So this reconfirms the information of phi2 naught and phi1 naught as the radiation part and as the Coulombic part in any given solution. The reason why I'm looking at real part of phi1 naught is because if I take the imaginary part, I will get the magnetic charge. But the way we do normally, if you have got the source current, then I mean, if the way we do normally is to say that grad A of FAB equal to FBC equal to 0. This says that there is no magnetic monopole. Magnetic charge vanishes. So this is where we are. That in fact, if I now wanted to go to sky minus, then all you have to do is to U goes to V, and so N goes to L. And so the peeling properties are actually just slightly changed, just because now the radiating part is going to be, because of this thing, the radiative part is in phi naught. Phi1 is still, because what I have to do is to change N and L. And therefore, that's why previously I had here for phi2 naught, the radiative part, I had an N here, so I had to put by L. But for phi1, I got N and L both. So if I flip N to L and L to L, I get the same. So therefore, the phi1 naught doesn't change, but this changes and this changes. And then the radiative part is now in phi naught. And so the radiation information is in here. So if we say that there is no incoming radiation, or if we are talking about retarded solution, then that means that this condition is 0. So this is the condition we use in gravitational waves, no incoming radiation. And in electromagnetic waves, that would say that phi naught naught is 0 at sky. Okay, so it is now about, I guess I should just go a little bit further, and then we'll quit, because I think I started just a little bit late. So I'll just go for 5 more minutes. And if there are questions, I'll take the questions. So the point is the following, that if I now look at a gravitational radiation, then I have to talk about asymptotical flatness at null infinity, because we saw that we really could talk about electromagnetic radiation quite nicely in terms of this cry, in terms of this asymptotic flatness, and now we want to do the same here. So the point is that we need to go far away from the sources. What are the difficulties? The difficulties are the following: that again, we need to go far away from the sources, exactly like in the Maxwell field. But there's no natural R coordinate anymore. So I don't know what I mean by going far away from the sources. What do I mean by that? And the distances are defined by GAB. And this is a dynamical field like FAB. In the Maxwell case, we had FAB and we had the metric eta AB. And then I could define R with respect to eta AB. But now the radial coordinate R dependence is to be talked about in terms of the FAB, in terms of GAB, which is a dynamical field in itself. There's no background to tell us what R means. And then secondly, what may look like time-dependent solution or time-independent solution in one coordinate system may appear a wave-like or undulating solution in another coordinate system, because, for example, there may be a time-like Killing vector field in one patch of space-time, but it really is like a boost Killing vector field and not a time translation. There's a very famous example. For those of you who are more advanced students, may want to look at this. It is called the Levitivator C Metric. And for the longest, it represents two black holes which are constantly accelerating. So there are two black holes like that. I got actually sky like that. They are like that. And they're actually radiating. But there is a boost-like Killing vector field, which is time translation. And therefore, for the longest time, people said that it is T-independent, and therefore there is no radiation distribution. So one had to actually use this null infinity construction to see if there is such a problem or there is no such a problem. And we did that in communication mathematical physics some time ago. So therefore, there was a lot of confusion about reality of gravitational waves that Einstein had first derived, first of all, using the quadruple formula in the linearized approximation. So Einstein had done this, in this approximation, showing how sources create gravitational waves. Time-changing quadrupole moment, mass quadrupole moment creates gravitational waves, but he used linearized gravitation. But in the until 1960s, there was considerable confusion on whether gravitational waves even exist. Are they physically real? There's big debates about this. And as we see next time, Einstein himself contributed to confusion here. And all this was clarified fully by Bondi, Sachs, and Newman and Penrose and others in the 1960s and 70s. And in the next two lectures, we will see this, what the mathematical foundation is, which actually provides the basis for all the current work in gravitational waves. So next time, I will tell you a little bit very famous story in which Einstein actually said that together with a young collaborator, I arrived at an interesting conclusion that gravitational waves do not exist in the full general relativity, though they had been assumed to be a certainty in the linearized approximation. And so therefore, all this goes to show is that we have to be very careful with coordinate freedoms in general relativity, and we need coordinate invariant notions of radiation, of energy, angular momentum carried by gravitational waves. And the null infinity that I talked about, Penrose's construction that I talked about, actually provides us exactly that. It provides us an arena, place on which to specify, to extract gravitational waves, to see if there are gravitational waves or there are no gravitational waves, to calculate how much energy and angular momentum and linear momentum is carried away by gravitational waves. So that is what we will do next time. I will stop here for questions. Are there any questions? I don't see any questions in the chat box, but maybe there are. No. So if there are no questions, what I would like students to write in your chat box, and I would like both advanced students, especially advanced students who want to learn more things about it, but also beginning students, just write in the chat box. Was this lecture understandable? Was it too easy? Was it too difficult? Was it about right? So just write it quickly. It'll take me all of you will take you 5 seconds to write it. So write in the chat box. You can just say it was too easy.
I think this lecture is very clear, and it's I think most students can digest it.
Okay.
Yeah. So and
may I ask a question, quick one?
Yes, please.
So in the maybe the last diagram, the integral for Q, the charge, and I guess next slide. What's the A plus? The notation besides the I plus.
Thank you very much. No, that was not A plus. It was supposed to be at scribe plus. It looks like A plus. You're right. It is just at. Oops.
Okay. I see.
It was just at. Thank you.
Okay, that confused me. Thank you.
Yeah, thank you. At, not A plus, right? It does look like A plus. You're completely right. So this U equal to U0 cross section is at scribe plus. So basically, you're looking at a cross section like that, U equal to U0. And I hope that these slides will be available, right? For the, what I'm going to do is to put one blank slide in case there are questions that I can answer the questions here. But since there are no questions, I'm going to remove the slide. So I hope these slides will be available to students over the weekend, so they can look at them and ask questions. And furthermore, the first paper that I gave you here, first reference I gave you, this one, it will have several. This reference will have some details, many more details than you necessarily need, but it will have some details that you'll actually be able to see what is going on. So this level is okay. So people, mathematical level is okay. Can some students write in the chat box, please? Like at least 4 or 5 students. There are 164, so 4 or 5 is not too many. Just say easy or difficult or okay. Just write these one of these three words, right? Each of you. Difficult, easy, okay. Because that will help me with the future lectures. There's some questions, sorry. So let me just answer this question and then go on. A question was, you started by discussing that Poynting vector is not invariant, but therefore you go to special infinity and utilize tetrad formulae. Would you comment more about why this treatment is eventually coordinate independent? Yes. So I think it will become much more clear next time. I mean, this is a good question. Here I explicitly use coordinate like u and r and so on. And I went to r equal to infinity. And this was to motivate the fact that what we want to do is to extract what we mean by 1 upon r part, 1 upon r squared part, etc. That's why we did. But really, we don't need to introduce these coordinates. In fact, that is one of the key things that we're going to see next time. That the definition of asymptotic flatness in general does not use r at all, does not use any coordinates at all. It is really completely coordinate independent. So I could have done this in a coordinate independent way from the beginning, if you like, but then people might find it too abstract, right? I mean, mathematical people probably would like that and would be very happy with it. But many of the physics people might find it too abstract. They would not be able to understand the connection. So what I did here is to really talk about the coordinate independence. The statement is that this phi 2 naught is actually Lorentz invariant. If whether phi 2 naught at scribe plus phi 2 naught, what I was referring to before was scribe minus. That's also true, but since we talk about scribe plus, this quantity is actually Lorentz invariant. And in fact, it's also going to be coordinate independent, as we'll see next time. This doesn't. So this is really Lorentz invariant quantity, and it doesn't have to do with which frame you're using to calculate it. But that is a good question, and hopefully next time you'll be able to understand better. But if not, ask again. So a lot of people are saying it was okay. Somebody was saying it was easy. Has non-locality of gravitational energy anything to do with the confusion about existence of gravitational waves? That's a good question. And the answer is no, not really. It was really much more, I mean, it's true that gravitational waves are there's no gravitational energy. You cannot locally define. There's no stress energy tensor associated with the gravitational wave by themselves, or gravitational field by itself. There's no local notion of energy, if you like. So in that sense, yes. But as we saw here, even in the Maxwell case, where we do have a stress energy tensor, we can talk about, how much energy flux or angular momentum flux or momentum flux there is across the surface. I can talk about that quantity. But, or how much energy momentum flux is there, which is a Lorentz, it's a 4 vector. So I can talk about that quantity in the Maxwell case. But in the gravitational case, the statement is that, in the Maxwell case, I can talk about energy momentum fluxes. So there is a local stress energy tensor, but still there is, it's not locally, you cannot still talk about what is a gravitational wave. To extract the radiation content, you have to go to infinity, even in the Maxwell case. So therefore, this really is much more. Somebody says, can you say once more why magnetic monopole is not included probably in the, yeah. So that is the kind of reason why I kept this extra slide, but now I'll put it back. So the question is about magnetic monopole and such thing, right? So in presence of sources, Maxwell's equations are not kind of symmetric between electric and magnetic part, because what we have is grad A, curl of FAB equal to 0. And then if you like, usually we write it as grad A of FAB. Or the way I wrote it was, it's completely the same, but just the way I wrote it was FAB equal to minus 4 pi times JB. Okay. I think one can write it better in that this can be written in a completely symmetric way. This is the same as saying that curl of star F BC is this is a dual. So this is just really the dual of minus 4 pi. So this is a 3 form, and this is the same as star B star G. So Maxwell's equations can be written like this is equal to 0. And then instead of this equation, I can write as grad A of star F BC equal to minus 4 pi of star JB. So, sorry. Okay, so this is Maxwell's equations up here. I can write them as just like that. Okay, or if you like, this equation is the same as. So I can erase this. Maybe that's better. I'm almost done. Just 1 second. So this equation you can write as d of f equal to 0 in the exterior form language, and this equation you say that d of star f. Actually, because of star, it turns out to be plus 4 pi, but that's not an important point. Okay, so you can see that there's an asymmetry. There is a 0 here, and there is no 0 here. If in fact you had an equation in which there was also something on this side, then you would find that there will be magnetic monopoles would be allowed also. So the usual way we say is that one of the components of this equation is the time component of this equation, if you like, would be dA EA equal to the electric charge density rho, right? Electric charge density up here, but dA of BA equal to 0. And this is why this implies that magnetic charge is 0, whereas here electric charge is equal to integral of rho d3x. Is this okay? Or I mean, I can do it more carefully if you like. Here is some source up here. I take a 2 sphere, and we talk about the electric charge. You know all that. The electric charge is, so this is the same as integral of E dot ds. This surface S, and the first line up here, charge, is just the integral here. This is the three-dimensional integral, three-dimensional surface. And what I do is to check the charge density and integrate on this three-dimensional surface. I'll get the charge, and the two are equal to each other because of this equation here. And of course, outside the sources, it doesn't matter which surface you choose. So it is this asymmetry in Maxwell's equations. Namely, I like to think really as this is the way to write the equations, and there is 0 here and there is no 0 here, and that is why we have a problem. I'm 1 minute over time. I just wanted to say thank you very much, everybody, and we will see you again on Monday. If you have questions beforehand, send them by email to Hong Chao, and then he can forward them to me, and I can address them next time.